everybody? Welcome back to Mr. Martin's Classroom. Today we're going to go over the topics of weight, mass, and density. To begin, we're going to talk about what matters, or what matter is. And we're going to talk about the difference between mass and weight. Although mass and weight are related, they represent two distinctly different physical properties. So mass is the amount of matter in an object, or the quantity of the inertia of the object. Mass is something that we measure usually with a device like a triple beam balance. Whereas weight is the force of gravity on an object. A scale, similar to what's found in the grocery store or doctor's office or in your bathroom, is used to measure weight. And the mathematical relationship between mass and weight is represented by this equation. Weight equals mass times the gravitational acceleration, where gravitational acceleration is 9.8 meters per second squared, or 32.2 feet per second squared, and that's constant on Earth's surface. It changes if you go to other planets, but for the sake of this class, we're going to be on Earth. We're going to do a quick example. So a man has a mass of 100 kilograms. What is his weight? So we can use that weight formula, and we'll multiply 100 kilograms times 9.8 meters per second squared, and that'll give us 980 kilograms times meters per second squared, which is called a Newton, which is a unit of force. So we're going to hop into another example. A woman weighs 100 pounds. What is their mass? So we're going to take our weight equals mass times gravitational acceleration equation and solve for mass. Plug in our information, so 100 pounds. And since we're dealing with pounds, we're going to use feet per second squared as our unit for gravitational acceleration. So 100 pounds divided by 32.2 feet per second squared. And that'll give us 3.1 slugs. Now, slugs are not commonly used because the pound is a more practical unit for commerce. As a result, pounds are often used to indicate mass instead of slugs. But since pound is a unit of force as well, there's often confusion about what the unit pound represents, and we're going to get into that more in the next few slides. Now we're going to talk about the difference between mass and weight. The avoirdupois pound, or pound mass, is defined as 0.4359237 kilograms, and it's a unit of mass. The slug is another accepted unit of mass in the U.S. customary system. However, because slugs are not well understood, it's become common to use the pound as a unit of mass as well as a unit of weight in the U.S. customary system. Unfortunately, as a result, mass and weight are often confused in the United States system, and many people do not understand the difference between the meaning of pound mass and pound force. Oftentimes, the context determines to which pound a person is referring. On the formula sheet, the pound force unit is indicated only with the letters LB. The pound mass unit is indicated with a subscript of M attached to the letters LB. Remember that mass and weight are not the same. Mass of an object is constant no matter what the environment. The force of weight changes with the acceleration of gravity, which can change as you move across the surface of the Earth or if you travel to another planet. Pound force is a unit of force. Weight is a force and is the result of the acceleration of gravity on the mass of an object. On the Earth's surface, we generally say, although not exactly, that 1 pound mass will weigh 1 pound force. This assumes an acceleration of gravity of 9.8 meters per second squared. However, the acceleration of gravity will vary from this value at different locations on Earth. Therefore, an object's weight will vary depending on where the object is located. Inconsistencies in weight measurements will occur among different locations. Thus, mass is preferred in scientific work. Unfortunately, in common practice, we've come to use the word pound to refer to mass and a force, and the meaning of the word can be confusing. On Earth, the mass of an object in units of pounds mass can change slightly due to differences in the acceleration of gravity, but is roughly equivalent to the force of gravity or weight of the object in units of pound force. However, because the mass of an object does not change, but the weight, force of gravity in an object is directly related to the acceleration of gravity imposed on the object, the weight of the object will change if the acceleration of gravity changes. For instance, if the object is taken into outer space or the moon. Next, we're going to talk about density. And density is the amount of matter per unit volume. So here's an example of high density and low density. So density can be indicated in multiple ways. We can talk about mass density, which is mass per unit volume, or weight density, which is weight per unit volume. On the equation sheet, there's both equations where mass equals volume times mass density and weight equals volume times weight density. The context of the situation will determine whether the density is expressed in terms of mass or weight. We're not going to worry too much about differentiating among the two at this point. However, it's important to be able to distinguish between the two terms of mass and weight and know the difference. So mass density is commonly used for SI units. So we have units like grams per cubic centimeter or kilograms per cubic meter. Weight density is commonly used for US customary units. We'd have pounds per cubic inch or pounds per cubic foot. Although density is often defined as the mass per unit volume, weight density is commonly used to express density when using US customary units. In the curriculum, density will refer to either mass density or weight density depending on the measurement device and the measurement system being used. The last thing we're going to talk about today is volume, which is the amount of three-dimensional space enclosed by an object. And we can calculate volume using the geometry of an object, so we can do a bunch of measurements and calculate things if it's a regular shape. Or we can measure indirectly using water displacement. So some volumes can be calculated, especially if they're regularly shaped. So spheres, for instance, they have a volume of 4/3 pi r cubed. Or rectangular prisms, you can find the volume by multiplying the width, depth, and height of the object. We can also measure the volume indirectly. So the volume of an irregular object can be determined with fluid displacement. We can record the water level in a graduated cylinder, add our samples that we wanted to determine the volume of, record the new level, and find the difference, and that would give us the volume of our sample. We're going to do a quick example where we're trying to find the density of a 2.24 inch diameter sphere of titanium that weighs 0.82 pounds. The first thing we need to do is find the volume of the sphere. The volume of the sphere we can find by multiplying 4/3 times pi times r cubed. Plug in 2.24 inches divided by 2 because we're given diameter and we need radius. And that gives us a volume of 5.88 cubic inches. Now we want to know the density. And we have this formula that weight equals volume times weight density. If we divide both sides by volume, we get that weight density equals weight divided by volume. We can plug in our volume that we just found and the weight which was given, and we get 0.82 pounds divided by 5.88 cubic inches. Put that into our calculator, and we get that the density of this titanium sphere is 0.14 pounds per cubic inch. Hopefully you found that helpful. If you have any questions, make sure you leave them in the comments below, and I'll hopefully hear from you soon.